All right, hello folks. Thank you for coming. I'm Simon. I'm one of the lead of vLLM project. And today I'll talk to you a little bit about vLLM, what we have been up to, what is happening, and then as well as some recent development and sort of the way we're thinking about the future of inference from the current point of view. All right, let's get started. So vLLM started as a research project, but quickly became the engine of choice for large language model inference. And our goal is to build the fastest and easiest to use open source LLM inference and serving engine. And to really look at it, vLLM, as I kind of mentioned as a keynote today, we really see it as an ecosystem where you have model, you have accelerator, and framework all working together. That is, from the model vendor point of view, vLLM is a trusted place and the engine of choice to implement the model in a most efficient way. And then from the accelerator point of view, as soon as they're able to add kernels for new models, it will broadcast, and any optimization will be able to benefit both the past and future set of 200 model architecture in vLLM. And then on the framework side, vLLM has been the go-to default rollout engine for a lot of RL framework today, as well as being used for reward modeling, synthetic data generation, and a lot more. And just to reiterate and dive a little bit deeper, the reason we're here today is that vLLM started on PyTorch and have a close relationship co-developing both vLLM and PyTorch together. And on the one side, vLLM really helped battle test a lot of PyTorch features, such as torch compile, flex attention, torch AO. On the other side, we leverage almost every extent of PyTorch library itself, such as plugging in our own memory allocators, or adding in new accelerator plugins, and as well as really abusing, in a way, torch compile to achieve the best inference speed possible. And the reason we're also here is we're part of the Foundation project. That is where we directly work with all the members of PyTorch Foundation to make sure that vLLM is being developed and openly governed by all the members and together to make sure that there's a longevity and shared governance of this project. And if you look at vLLM progress so far, we're fortunately enough, as of last week, we have, of course, 60,000 stars, as well as 800 PRs being merged every month. And to manage this project as a scale, we cannot do it without a lot of industry partners such as Meta, Red Hat, Anyscale, Hugging Face, and a lot more companies that directly focus on working on the open source upstream vLLM, supporting different models, supporting different hardware, and then making sure that you're getting the best optimization on the newest frontier model. Let's look at the code a little bit. So this will help us anchor around the conversation about the newer feature that we're recently introducing in vLLM. So there's two ways to use vLLM. One is to use it as almost a drop-in replacement for Hugging Face transformers inference, where instead of running batches at a large batch with padding, we offer continuous batching with the LLM interface. The LLM interface allows you to initialize a large language model and directly run through your list of prompts. This prompt can be millions of entries if you need to be. The other way is to use it as a server. You can use it as a drop-in replacement for OpenAI server, or anything that speaks the SASTRA protocol. And this is where you can directly target your application that's designed to talk to OpenAI protocol today to talk to vLLM. And with that, unlock you to all the open source large language model. And this piece of news that's so new that we actually didn't get to put on the slide is that as of this morning, we just merged support for the Anthropic API. So now you can point your Claude code and related application tied to Anthropic protocol to directly talk to an open source model as well. And we're going to see more and more usage down the line for this. And additionally, as I mentioned before, this is the two primary way of directing using vLLM. But as we build the end-to-end system, we also support a way to break it up apart, so that a lot of frameworks are directly leveraging internals of vLLM and or lower level abstraction and construct to directly use it to integrate into their existing framework and applications. And just to talk a little bit more about the model we're serving, a lot of times we directly work with people who are making the model and training the model and open sourcing them directly. And a lot of cases you see what we call day zero support. And this word day zero support really just means the moment that the model weight went down to be public on Hugging Face Model Hub or any other places, you are able to download and run it with vLLM. And of course, this is not magically happening. Like the moment the model release and we get to work, it is a long relationship we're building with all the model vendors across both China, US, and around the world to make sure this is happening. And for models that do not have a direct relationship or directly have bandwidth to work on, the great news here is we have worked with Hugging Face to support what we call transformers backend. And this allows you to have one flag in vLLM Serve that plug into models that do not yet have native support in vLLM, but you can directly run it with transformers implementation. This also comes with a great benefit that you can have the same piece of code, the same model definition to be used between pre-training, RL, as well as inference. It's the same Hugging Face model definition code. And we also have state-of-the-art vision and language model support. We have recently got on a lot of headline with our support for DeepSeek OCR system, as well as Queen3 VL. We're seeing that our design architecture support you to add new modality quite easily. And this is just a start. So you can use vLLM to do OCR task, vision understanding, but later on, we're quite excited to start supporting like multimodal output, such as image generation in the vision transformer style. And speaking of model support, we prioritize accuracy quite a lot. If you ask me how much time did I spend actually, do we spend on supporting GPT-OSS, which is the model from OpenAI, when we spend 30 days with this model, 20 or more days are spent on making sure that we get exactly the same bits of log probabilities output directly out of the model, so that you are actually getting the model that you are intending to get, not some sort of version that will have silent corruption bug or accuracy issue. And with that, just today, we have announced that the support for batching variant mode. So this is a long time in the making in collaboration with Thinking Machine Labs as well as Meta to support that regardless how many requests is in the batch, regardless of the batch structure, the ordering, you are able to get exactly the same output over time. And this actually has been the case strongly used to verify accuracy, especially to make sure that your model is exactly what you're getting from the training framework as well. And accuracy is one part. The other part is we prioritize performance. There's a lot of ways to tell you about this, but one way I find liking is instead of showing the performance bar chart, is that we actually invest a lot. So on the left, it is a nightly performance dashboard that we work together with the PyTorch developer team, that we actually run every single commit, run through an extensive set of tests to make sure there's no performance regression, and it will only get better. And on the right side is really talking about how much this costs in terms of funding and the infrastructure to use to provide performance guarantee. And just to speak a little bit more on the PyTorch and vLLM, one thing I think we didn't mention is there is large production use cases running on the nightly of vLLM on top of nightly of PyTorch. And this really ensures that as the most cutting edge, where you can get the most performance possible, that is being validated and being run. And this is why you see a lot of GitHub issues and PRs popping up on vLLM talking about, wait, the current main is broken on PyTorch nightly that hasn't been released and will be released in 3 months. Because 3 months before you get the new PyTorch release, we're already making sure it's working. And of course, this is just the first series of talk, that there's a lot more talking about vLLM during the PyTorch conference. And now I'm going to spend a few slides talking about the new technical insights that we're developing on in account for the new trend that we're seeing today. So I'm going to first talk about a little bit a summary of 2 techniques, and then interfaces. And then later, I'll dive into the work I've been doing on distributed inference. So the first technique is what we call hybrid allocator. So if you are seeing the trend of model going forward, we started with just dense transformer like Llama and Qwen dense, and then gradually moved toward MLE like Mixtral, and then later moved towards larger MLE like DeepSeek and Llama 3, Scal, and Maverick. But then that's how the FFN is happening, but the other side is attention. On the attention side, we're actually seeing quite a lot of innovations, beyond just the typical multi-headed attention, we have been seeing MLA, multi-latent attention from DeepSeek. But then people are actually innovating on improving the quadratic behavior of attention mechanism. So that's why we started building a system called hybrid memory allocator. The hybrid memory allocator allows you to efficiently manage the KV cache for a model with hybrid memory requirement, such as a model with sliding window and full attention, or the sliding window, full attention, and Mamba or state space model blocks. And we allow you with different kinds of intricate design to be well managed and efficiently served. The second part related to KV cache is the emerging need of KV cache transfer as well as storage. So as KV cache as the context gets bigger and bigger, you have a higher need to manage the KV cache to move it around. Take example of a 1000K context window. The memory bytes required to manage that KV cache is quite big. And recomputation sometimes is going to be slower than just moving that, caching it in CPU or remote storage and bringing it back on. This is why we, in collaboration with the team at LM Cache and other, we built an interface called KV Connector. So in vLLM, now we can support offloading the KV cache, compressing the KV cache, and as well as transferring KV cache in multiple ways. So for example, you can store the KV cache in your accelerated storage in Weka, or you directly move it to CPU RAM for later usage. And then one more bit on a new innovation we're seeing, again, related to KV cache and attention, is as attention is getting more and more efficient, you typically see a straggler effect when you are serving at large scale. What does that mean is if every single GPU is running its own request, sometimes there's one request with a lot of input tokens that would just slow down everybody else. And this is why, in collaboration with the team that's behind Kimi K2, the world's sort of first modern transformer 1 trillion parameter model open source, that they have open source what you call decode context parallel. Decode context parallelism is something that allows you to shard and stripe the input context across different ranks. And this is a new parallelization degrees compared to tensor parallelism, expert parallelism, and many more. This really allows you to resolve the straggler problem. And then you can see that if you use this model to use this way to serve DeepSeek v3.1 with decode context parallel, you will immediately get a lot more KV cache space as well as better throughput. All right, just to recap of the session we just mentioned before, vLLM makes sure we are delivering timely, accurate, and optimized model support. We also have a wide hardware coverage going from latest generation NVIDIA chip to AMD to Intel and a lot more, as well as flexible API with variety of integration with our framework, and deeply integrated PyTorch and frontier of innovation of many techniques. Now, I'm going to dive a little bit more with distributed inference. That is a core focus of us over the last few months, that to focus on while vLLM can make the job, can do the job of serving a single model on a single group of GPU really well, what are you doing to scale it up? And this is where the different ways of thinking about distributed come in. One way to think about it is there is from the engine out perspective. That is, we can think about different parallelism, think about fault tolerance, think about elasticity. vLLM does all that. Another way of thinking about it is from the cluster in. From the cluster management point of view, especially someone who have been managing thousands of GPUs at large scale or even more, you actually need to worry about routing, caching, and operation. And this is where LMD comes in as a community project to focus on really gluing together the cluster operator perspective as well as the inference engine perspective. So the way you look at it is the world of Kubernetes, that a lot of it is designed for microservices, where it is processing requests that are fast, uniform, and cheap. But on the other side, LM inference is orders of magnitude more expensive, way less uniform, and require a lot more acceleration and consideration from the cluster point of view. And LMD really helps this by deeply integrating with Kubernetes primitives, such as when the request comes in, you'll go through the inference gateway, and you're able to intelligently choose and route to different LM instances, vLLM instances on different hardware. And this also provides quite a lot of reproducible samples. one challenge we had, if you asked me a year ago, is that you really cannot scale vLLM in a reproducible manner. Every cluster behaves differently. Everyone have different requirement network topology. And sometimes when we say we can get, let's say, 2,000 tokens per second on this setup per GPU, someone else cannot get it. But then LMD, by building on top of Kubernetes and primitives, this really help our community with different well-lit paths that is directly reproducible and tweakable so that you can directly bring it into your setup. And this includes intelligent inference scheduling, PD disaggregation, KV cache management, and wide EP. I'll quickly illustrate a few of them. For intelligent inference scheduling, this is a way of framing this problem as a smarter way of routing requests and load balancing the request. So the way you deploy vLLM in a distributed manner today is one, you can just put it in Kubernetes services and perform round-robin load balancing. And this typically is pretty bad in the sense that because different requests is such a non-uniform fashion that you don't really get the best balanced approach. And LMD supports prefix-aware routing. So on the left, you can see that you'll match to the right prefix tree so that you always have lower time to first token when the request has already been processed. On the other side, there's load-aware routing, where you'll be able to scrape and intelligently analyze vLLM-specific metric to route to the right pod. On the PD disaggregation, LMD, along with the vLLM integration itself, provides a way to efficiently transfer from GPU to GPU, leveraging NVIDIA Nexo library, as well as a counterpart of what will happen in AMD and TPU, to be able to directly transfer the KV cache from the prefill instance to the decode instance. And by separating prefill and decode, this allows you to run different parallelization strategy and deployment option and scaling across the two. And finally, there's wide expert parallelism. The way you typically serve the 1 trillion parameter model today is not getting a GPU has 1 trillion, getting a node with 1 trillion bytes in memory. Rather, is you actually scale it out into way bigger pool. And this allows you to efficiently manage a large batch of requests and distribute it up across multiple ranks. And this is where LMD allow you to have a way to directly, easily manage this on top of Kubernetes, again, so it is more reproducible and easily usable. And along with this, we have leveraging optimization from the DeepSeek team, where such as performing expert parallel load balancer, where you can move the expert within the model, move them around, replicate them, so that you can achieve a great utilization score. As well as dual batch overlap. This is, again, work inspired by what DeepSeek has been working on to run communication and computation overlapped to make sure that in this large distributed fashion, every part, the network, the memory bandwidth, and then the compute are all well utilized. And that's pretty much it. So now I have covered vLLM a little bit. I've covered our recent development, and now I cover our distributive. And to really think about the roadmap is really much a doubling down on all that. But I have a few minutes, so now I can take questions. Thank you so much. I don't think we have a mic runner, so just shout, and then I'll try to repeat the question. Yeah.
All right. So the question is, if you want to integrate with vLLM as a different accelerator.
Yeah.
Previously, it was completely PyTorch-based from what I looked at. Has things changed? Like, do we need to rely on PyTorch for this accelerator, or can we have our own runtime and use it?
Yeah, so the question is about the experience of adding new accelerator, how strongly tied it is with PyTorch. So vLLM does require PyTorch, but what we do offer now is a plugin mechanism where you can swap out what we call the model runner and the model execution path. So within vLLM, PyTorch is the framework that you're using, but outside of it, when you're adding your own hardware, you don't really need your hardware runtime and software stack to directly work with every single operator of PyTorch. Rather, you can take the PyTorch graph, go through the Torch 2.0 compile inductor path, and lower it to whatever framework or language you like. And this is one of the ways that later you'll hear about the vLLM TPU story. When for vLLM TPU, initially they started with Torch XLA, but now, as of a week ago actually, the version they announced is actually lowering PyTorch model definition to JAX. And then JAX will be able to run it on a higher utilization on TPU. So for any new hardware, you can actually do pretty much exactly the same thing to lower a PyTorch model definition into whatever language and framework and compiler of your choice. Thank you. Yes?
So my question is mostly about the optimization part, and you mentioned that you guys also have serving for vLLM, like some own LLMs and stuff. So my question is, like, you shard the LLM across multiple GPUs, like break it down to smaller shards, and if you guys do that, then how do you ensure that the first token that is tokenized by whichever GPU? So how do you guys ensure that each token is done done concurrently or done more for every batch?
Yeah. So the question is, in different kinds of parallelization paradigm, how do we make sure there is correctness where tokens are routed to the right rank, as well as, I guess, performance where this is well served? And what the job of vLLM is to ensure that we have a lot of options to scale it out in a different fashion. So initially, vLLM only have tensor parallelism, and this is when the token come in, it's kind of broadcasted to all ranks, and then internally, across the intermediate and hidden dimension, you are doing all sorts of collected to make sure it can continue to run. And then there's pipeline parallelism, where you shard the model layer by layer across different nodes. And then later we added context parallelism, as I mentioned. That is really sharding the token across different rank and making sure that the attention will add up in the end with zero accuracy loss. And then, of course, expert parallelism and a lot more coming down the pipeline to make sure that we are separating and sharding the model in a different way. But correctness is never a sort of a thing you sacrifice and trade-off. Rather, distributed way is the way to really make sure that you can run it at a larger scale at a greater efficiency. Cool. Yes?
How does prefix-aware routing and load-aware routing work together in AI?
Great question. How does prefix-aware routing and load-aware routing work together? So they don't. Sometimes they are a choice. Sometimes they do in a way that here's what happens under the hood. Prefix-aware routing requires expensive computation and reconstruction of the prefix tree. So that requires you essentially understand every string and every token that happens there. And then load-aware routing is where you essentially have statistic averages over the KV cache utilization. And in a lot of cases, you actually choose one way or the other depending on P or D. And then whether or not you are working on prefill or you're working on decode. But in different cases, depending on your production environment, you might actually mix the signal of the two. Fundamentally, the choice of the endpoint picker, that's in the LMD construct, or the load balancer itself, is the one that you have to choose the host to send the request to. And it is a matter of how do you compose or choose or select the right algorithm to deliver the token over there. Cool. I think we'll have 1 more minute over there. Yes? So just to confirm, because I have trouble hearing, is about the numerics and batch invariant, right? Or training inference consistency, is that? OK, yeah, so the question is about share more about the training inference consistency. And the way we typically approach this problem is, given the same number of GPU, right, given the same distributed setup, and given, of course, the same model weights, we want to make sure that in the end, you are getting exactly the same under a condition that is, if we get to use the same kernel or same distribution strategy, you are going to get the same output. But this is fundamentally difficult because in attention, especially in inference engine like vLLM, we do what you call page attention and continuous batching. And this is different from the training paradigm where you actually pad all the requests together and put them in one batch. So if you put them in one batch and run it, and then we want to make sure that in a continuous batching scenario, we're getting exactly the same output as well. So that actually requires a lot of tricks with kernels, with tuning distributed computation. And again, for that, I highly recommend the blog from Thinking Machine Labs to talk about batching invariance. And it's from Horace. Horace might be here today as well. All right, cool. I think we're out of time. I'm happy to take questions off the stage. Thank you so much.